Hello, everyone. My name is William Goodman, and I'm here to talk about the hydrogen economy today. So, what is the hydrogen economy and why is it needed? As anthropogenic activity continues to heavily impact the climate, the need for a decarbonized economy is becoming more and more apparent. The sheer magnitude of this task is difficult to put into words, though it is clear this transition will require a combination of multiple technological advancements, fundamental change across many industries, and a reimagined global power grid. The hydrogen economy is a hypothetical future in which we meet the needs of society while using hydrogen as a fuel source. More specifically, it's an economy in which we've replaced fossil fuel use with the use of hydrogen gas. So, the color coding of hydrogen is important, as this is how we determine how the hydrogen was produced. Gray hydrogen is a form of hydrogen that is derived from fossil hydrocarbons and is often the result of steam methane reforming of a natural gas. And it currently accounts for around 96% of commercially produced hydrogen, according to the World Energy, the Energy Research Partnership. The byproducts of this are monoxide and carbon dioxide, and it's while this method is very cost effective, it is far from sustainable due to the aforementioned associated carbon emissions. For every ton of hydrogen produced, this method also produces 9 to 12 tons of carbon dioxide, depending on the quality of the feedstock. Green hydrogen is produced via the electrolysis of water, a clean process which does not emit any carbon. Currently, 4% of hydrogen produced globally stems from electrolysis. Electrolysis is the process of splitting water into H2 and O2 by applying electricity through an electrolyzer. In order to qualify as green hydrogen, this electricity needs to be sourced from renewables. So, what makes hydrogen unique? Well, hydrogen has many key differentiators to separate it from other proposed solutions. Hydrogen is unique in the sense that it has the potential to address core issues within a variety of industries, even those that have generally been viewed as sustainability laggards. Hydrogen is also unique in the sense that, like electricity, it is clean at the point of use, but unlike electricity, it is storable. Finally, hydrogen is abundant and evenly spread across the globe, meaning that no country or group of countries can control its supply. So the capability to store hydrogen is a key aspect of its potential as a tool to decarbonize the global economy. Without these storage capabilities, significant innovation in hydrogen technology as it applies to transportation or power generation would not be feasible. Hydrogen gas has a low volumetric energy density relative to natural gas, meaning that storage techniques are vital for its success. There are many methods of storing hydrogen, each has its advantages and disadvantages. The three main methods are as a compressed gas, as a cold liquid, or through the oxidation of metals. The most common method involves a compressed gas, putting compressed hydrogen gas in a pressure tank, and this pressure can reach up to 80 megapascals. The weight of these tanks is a concern, however, new lightweight composite fiber tanks can withstand the prescribed pressure. Underground salt caverns have recently begun attracting attention as large-scale storage for hydrogen. It can be stored at a liquid ambient pressure of minus 2,500 degrees Celsius in cryogenic tanks. This method will increase the volumetric density of hydrogen, though the highest volumetric density is achieved when hydrogen is absorbed through the interstitial sites of a host metal. Hydrogen can also be stored through the oxidation of various metals, including lithium or sodium or zinc. This method is attracting attention because it can hold 2 hydrogen atoms for every metal atom. The variety of viable storage methods is complements the range of use of hydrogen. Sorry. So the industries hydrogen can impact: transport, heating, and power. Transport is responsible for approximately 20% of the worldwide CO2 emissions. This stems from internal combustion based engines burning fossil fuels being used by passenger vehicles, freight trucks, airplanes, and ships. Fuel cell vehicles, which can run on hydrogen, are beginning to attract attention from private investors. Though there are many different varieties, a hydrogen-based fuel cell generally works by converting the chemical energy of hydrogen and an oxidant into electricity while emitting water vapor and heat. The current market for fuel cell vehicles is small. Presently, most fuel cell vehicles are simply part of demonstrations. Globally, there are only 200 refueling stations, so infrastructure is a major concern, as well as the associated fueling costs, the transportation of hydrogen, and the combustible nature of the gas. In terms of heating homes and water in businesses and domestic homes is a major source of CO2. It accounts for approximately 10% of emissions in the United States. Proposals to electrify our heating systems are gaining steam, though this presents many challenges as demands for heating vary greatly throughout the day. Due to this, storage becomes indispensable, and as we are not currently capable of storing electricity at scale, A power grid sourced purely from renewable energies faces many obstacles. Hydrogen, which will be heated in a boiler, offers many benefits. Firstly, carbon emissions associated with heating of homes and water, as well as cooking, would plummet. Using green hydrogen as an intermediary, it is possible to source the heating of home from renewable energy sources. Secondly, this could be implemented within the existing gas framework. Since the hydrogen boilers are similar in size to gas boilers, implementation would not require large-scale disruption. Gas boilers are even capable of burning a mixture of hydrogen and natural gas after slight modifications. Additionally, hydrogen is more energy dense than natural gas, as roughly 1 kilogram of hydrogen contains the same amount of 2.8 kilograms of gasoline. However, natural gas is a higher volumetric density. The third major benefit stems from hydrogen's ability to meet the fluctuating energy demands due to its storage capabilities. So, the economic viability of green hydrogen. Currently, green hydrogen is not economically feasible due to the cost of producing electricity necessary to conduct electrolysis. The whole cost of producing green hydrogen, about 50% of it comes from the electric input during this process. This electricity is produced from renewable resources, most commonly wind and solar, and both of these methods have and will continue to see drastic improvements in their total capacity. The cost of both of these has been dropping consistently for the past decade, a trend that experts agree will continue. As you can see from the graph here, both solar and wind energy are expected to plummet in price within the near future. So while predictions vary, Morgan Stanley has estimated the price of green hydrogen will drop by up to 70% by the year 2030, at which point it will become economically competitive with gray hydrogen. In terms of global investments, the European Union leads the way. It has invested billions of dollars, and by 2050, it expects renewable hydrogen energies to be scalable enough to employ a large-scale decarbonization of its economy. So in conclusion, the hydrogen economy has massive potential. It is dependent on wind and solar energy becoming cheaper, and its unique characteristics make hydrogen a prime candidate to massively overhaul our energy system and address core sustainability issues within a variety of industries. Thank you all for listening. Does anyone have any questions?